All right, so today we're going to continue our review class. So in the previous class, Benno solved for your first problem in the practice exam, and you can see that the structure of the practice exam is like in the real exam. So in first questions, you're going to have to solve the eigenvalue problem, all right? So this eigenvalue problem is a little bit difficult, but in exam it's going to be easier, all right? Because in this eigenvalue problem, what you have to do is to solve the characteristic equation, and the characteristic equation in this practice exam is the real one, where you have you have x squared plus ax plus b, and a and b are different from 0. All right. So in the real exam, it's going to be a little bit easier. Right. So now in the second problem, what we have to do is to solve the real boundary value problem, which is the following. So problem number 2, you have to solve the equation u second plus x is equal to 0 or minus 1, 1 with the boundary condition u minus 1 is u1 and u prime of minus 1 is going to be u prime at 1. All right? So basically this is the boundary value problem that you have to solve. All right? So you have to solve u second plus x is equal on minus 1, 1. All right? And u minus 1 is u1, and u prime minus 1 is u prime of 1. So step number 1 is to solve the boundary value problems. All right? So step number 1, to solve the eigenvalue problem. Eigenvalue problem. All right, so the eigenvalue problem will be the following. So you have phi second plus lambda phi is equal to 0, and phi of minus 1 is phi of 1, and phi prime of minus 1 is equal to phi prime s1. So basically this is the homework, right? So this is one of the questions that we have in homework. And when you solve this, I'm going to show you in a couple of minutes that you're going to find the basis that you have for the Fourier series. All right? So basically, the equation here that you have is basically a Fourier series problem. All right? So this is basically the eigenvalue problem that you have, and now you have to solve it. So the first step is to do what? Characteristic equation, right? So the characteristic equation is going to be lambda squared, x squared plus lambda is equal to 0. All right? So this is the characteristic equation of the eigenvalue problem. All right? So this eigenvalue problem is easier than problem number 1 in the practice exam, because the characteristic equation is just x squared plus lambda is 0. All right? Now, we have to consider 3 cases. All right? Case number 1. Case number 1, lambda is smaller than 0. All right? So when lambda is smaller than 0, you're going to have x squared is equal to minus lambda, which is the absolute value of lambda. All right? Which is greater than 0. All right? So I explain again. So I give you a boundary value problem. You have to follow the 3-step scheme, all right? So the first step is to solve the eigenvalue problem, and this is the eigenvalue problem you have. You have phi second plus lambda, phi is 0. So now you have a characteristic equation which is x squared plus lambda is equal to 0, all right? So in order to find eigenvalue problem, you just throw away the source term, right? So you have u second is minus x. This is the source term. And this is the operator. All right? So So in order to find the eigenvalue problem, you just forget about the Stokes term, you look into the operator, and you solve this equation. It's clear? Now, for this eigenvalue problem, you're going to have a characteristic equation, which is x squared plus lambda is equal to 0. All right? So case number 1, lambda is negative. When lambda is negative, you have x squared is minus lambda, which is also the absolute value of lambda. All right? So now you're going to have two solutions, two roots. So you have R1 is square root of the absolute value of lambda, and R2 is also minus square root of lambda. All right? So for this eigenvalue problem, for this characteristic equation, you have two roots. The first one is square root of lambda, and the second one is minus square root of lambda. Right? Straight. Now, which means that you have two solutions. All right? So you're gonna have u1, which is exponential of square root of lambda x, and u2 will be exponential of minus square root of lambda x. All right? So, all right, it's clear? So for this problem, you have two roots. The first one is square root of lambda, and the second one is minus square root of lambda. So the two solutions will be exponential of square root of lambda, and the second one will be exponential of minus square root of lambda x. It's clear? Questions? So now the solution will be, the general solution will be is phi x will be the linear combination of u1 x plus c2 u2x. All right? And this is going to give you c1 exponential of square root lambda x plus c2 exponential of square root lambda x. All right? So I have a remark that some of you asked me, what is exponential? So exponential of t will be e to the t. Right? So this is a notation that I use. So exponential of t is the same with e to power t. Right? So I explain again. So in this case, you have an eigenvalue problem, which is phi second plus lambda phi is 0. So then you're going to have a characteristic equation, which is x squared plus lambda is 0. So this gives you two roots, square root of lambda and minus square root of lambda. All right? So then you're going to have exponential of square root of lambda and exponential of minus square root of lambda x. The solution will be c1 of u1 plus c2 of u2. So c1 and c2, they are two constant. Right? So a remark is that exponential is t to power, is e to power t. Right? So c1 and c2 are constant that we need to find. All right? So c1 and c2 are two constants that you have to find using the boundary condition. All right? So now you're going to use the boundary condition. Boundary condition. So the boundary condition is phi 1 is equal to phi of minus 1. All right? Which means the following. So you have c1 exponential of square root lambda plus c2 exponential of minus square root lambda is equal to c1 exponential of minus square root lambda plus c2 exponential square root lambda. All right? So the first boundary condition says that this is boundary condition, right? So this is the boundary condition that I'm using. So and phi 1 is equal to phi of minus 1. All right? So I replace 1 here. I'm going to have c1 exponential of square root lambda plus c2 exponential minus square root lambda. Because here I have 1 and 1. All right? So this is going to be phi of minus 1. So I replace minus 1 here and minus 1 here. I'm gonna have C1 exponential minus square root of lambda, and here because here I have minus 1, so I have C2 exponential of square root of lambda, right? It's clear? Questions? Now I'm gonna see that here you have the same lambda, right? And here I have this one. So I'm gonna group them together. So I have C1 minus C2 exponential of square root of lambda is equal to C1 minus C2 exponential of square root of lambda. Alright? It's clear? So now, because after I have the characteristic equation, I can find two roots. The two roots give you two solutions. And the general solution will be the linear combination of the two solutions. So what I'm going to do now is to plug in the boundary condition to find the two constants. Alright? So now I have phi1 is phi of minus 1. Phi1 is C1 exponential of square root of lambda, which is here, plus C2 exponential of minus square root of lambda, which is here, and this is phi of minus 1. So phi of minus 1 will be, I'm going to replace x to be minus 1, so I have C1 exponential of square root of minus square root of lambda, and here I replace minus 1 here, I'm going to have C2 exponential of square root of lambda. Alright? So I have this equation. I want to find C1 and C2. So I see that here I have exponential of square root of lambda, and here I have exponential of square root of lambda. So what I'm gonna do is I group them together. Alright? So I have C1 minus C2. So I'm gonna put this term to the left hand side. I have C1 minus C2 exponential of square root of lambda. Alright? I'm gonna here I have exponential of minus square root of lambda, and here I have exponential of minus square root of lambda. So I'm going to have C1 minus C2 exponential of minus square root of lambda. Alright? So I put them together. So now what I have is C1 minus C2, and here I also have C1 minus C2. Alright? So which means that C1 minus C2 exponential square root of lambda minus exponential of minus square root of lambda is 0, and this means that C1 is equal to C2. Alright? So I group them together, and I'm going to have C1 is equal to C2. Questions? It's clear? Alright, so now I'm going to check the second boundary condition. So now I have C1 is equal to C2, right? Which means that phi x will be C1 exponential of square root of lambda x plus C1 exponential of minus square root of lambda x. Alright? So from the first boundary condition, I infer that C1 has to be equal to C2. Alright? So I replace C2 by C1, so this is basically the general form of phi. Questions? It's clear? So now I'm going to have phi prime of x will be C1 square root of lambda x exponential of square root of lambda x. And here I have minus C1 square root of lambda exponential of minus square root of lambda x. Alright? So from the first boundary condition, I find that C1 and C2, they're equal. Alright? So I replace them here. So I replace C2 to be C1, and I'm going to take the derivative. When I take the derivative, I'm going to have C1 square root of lambda, and here I have minus C1 square root of lambda. Alright? It's clear? Right, so now I'm going to use the boundary condition 2. So I'm going to have phi prime at 1 is going to be phi prime at minus 1. Alright? So phi prime of 1 is equal to phi prime at minus 1, which means that C1 square root of lambda exponential of lambda is equal to exponential of minus square root of lambda is gonna be C1 square root of lambda exponential minus square root of lambda minus C1 square root of lambda exponential square root of lambda. Alright? So I'm gonna use the boundary condition number 2. Right? So this is the second boundary condition and this is the first boundary condition. Alright? Now when I use the second boundary condition, what I have is C1 square root of lambda exponential square root of lambda. Because here I replace x with 1, here I replace x with 1. So on the left hand side I have this term. So on the right hand side I have minus 1. So here I have minus 1. So this is why I have minus square root of lambda here. And this is minus 1. So when I replace it here, I have exponential square root of lambda. Right? Questions? So I'm going to see that here I have lambda. So I'm going to remove all of the lambda. Alright? So I'm going to have C1 exponential of square root of lambda minus exponential of minus square root of lambda is C1 exponential of minus square root of lambda minus exponential minus square root of lambda. Right? So I'm going to remove all of the square root of lambda. Right? So now I have C1, because here I have C1, C1. So I put everything into C1. So I have C1 exponential square root of lambda minus exponential minus square root of lambda. So on the right hand side, I'm going to do the same thing because I have C1 here. So I have C1 exponential minus square root of lambda minus exponential square root of lambda. Right? But this is minus this one. So I'm going to have 2C1 exponential of square root of lambda minus exponential of minus square root of lambda. And this gives me 0. So basically C1 is 0. So C2 is also 0. So which means that phi is 0. And this is trivial solution. Right? So in the case when lambda is positive, is negative, you have a trivial solution, and then there is no eigen function or eigenvector. Alright? So when the solution is 0, you don't admit it because you cannot have an eigen function or eigenvector which is 0. But if lambda is 0 and the function, the solution is different from 0, you still admit it as an eigenvalue and an eigen function. It's clear? Questions? So you understand the first case, right? Questions? It's clear? So now, basically this case is always the easiest case. And the modifiable case is the next one, when lambda is 0 and lambda is positive. Right? So now I consider the case when lambda is 0. So case number 2, when lambda is 0. So what you have is the following. You have phi second of x is 0. And then you have two boundary conditions. Phi of 1 is phi of minus 1. And phi of prime of 1 is phi prime of minus 1. Alright? So the case when lambda is 0 is easy, but it doesn't give a solution which is 0. So in this case, you still have an eigenvalue, an eigenvector or an eigenfunction. All right. So second case, lambda is 0. So when lambda is 0, because lambda is 0, you have phi second is 0 with the same boundary condition. Questions? It's clear? So when phi second is 0, right? When phi second is 0, so you have phi prime should be I, right? So phi second is 0, means that phi prime will be the antiderivative of 0, which is a constant. Alright? And this gives you phi x is ax plus b. right? So this is the procedure that we go over several times in the previous classes, all right? So when phi second is 0, you have ax plus b. Now you have to use the boundary condition, all right? Boundary condition. So you have phi 1 is equal to phi of minus 1, which means that a times 1 plus b is equal to a times minus 1 plus b. So you can remove the 2b on the two sides, so you have 2a is 0, which means that a is 0. All right? So I'll explain again. So because phi second is 0, phi has to be a linear function. So phi is ax plus b. All right? Now you're going to use the boundary condition. You have phi 1 is phi of minus 1. Right? So you have a times 1 plus b is a times minus 1 plus b. So you remove the 2b. So here you have a times 1. Here you have a times minus 1. So I put this one on the left hand side, and 2a is 0, which means that a is 0. All right? So the solution will be px will be only b. It's clear? So now I'm going to use the second boundary condition. Right? So phi x is b means that phi prime of x is always 0. So phi prime of 1 is going to be 0, and this is going to be phi prime at minus 1. All right? So finally, when lambda is 0, all right, phi is b, and this is a constant, right? So since phi x is any constant, the Eigen function is 1. All right? So in the basis, you can remove all of the constant. So in this case, the Eigen function is 1, or the Eigen vector, right? Eigen vector is 1, and the eigenvalue is 0. All right? Questions? So I explain again. So case number 2 is also easy, but it's going to give you one eigenvalue and one eigen function, eigen vector. All right? So when phi second is 0, you have a linear function ax plus b. You check with the first boundary condition. You have phi 1 is phi minus 1. So which means that a times 1 plus b is a times minus 1 plus b. So you remove the 2b, you get a is 0. Which means that the solution is always a constant. All right? So now you check with the second boundary condition. But because the function is now constant, the derivative is always 0. So which means that the second boundary condition is always satisfied. In other words, the solution for this one are a constant function. All right? Because they're all constant, you can remove a constant. Right? So the eigen function is 1. And then in this case, lambda is 0, which means that the eigenvalue is 0. Right? So in this case, you have one eigen function or eigenvector and one eigenvalue. Questions? So now, the most difficult case is the case when you have sinus and cosinus, and normally this is the case when you can find all of the others, all of the eigenvalues and eigenfunctions of the solution, of the equation. So now I'm going to go to case number 3. So case 3, you have what? You have x lambda is positive, so x squared plus lambda 0 implies that x squared is minus lambda, right? And the two roots will be the two root R1 will be I square root of lambda, R2 will be minus I square root of lambda. All right? Questions? It's clear. So in this case, what are the two solutions?
Cosine squared of lambda, cosine squared.
Right. So the two solutions will be U1 is sinus of cosinus square root of lambda x, and U2 will be sinus of square root of lambda x. All right? So, I'll explain again. So in the last case, lambda is positive, so you have x squared plus lambda is 0, which means that x squared is minus of lambda. All right? So you have two roots. So in this case, because lambda is positive, you have two complex roots. You have I square root of lambda and minus I square root of lambda, which means that you have two solutions, cosinus square root of lambda x and sinus square root of lambda x. All right? So the solution will be a linear combination of U1 and U2. And this gives you C1 cosinus of square root of lambda x plus C2 sinus of square root of lambda x. All right? So we need to find the two constants C1 and C2. All right? It's clear? So I explain again. So in the last case, because lambda is negative, lambda is positive, you have two complex solutions, I square root of lambda and minus I square root of lambda. All right? So this gives you two solutions, cosinus and sinus. All right? So you have cosinus square root of lambda and sinus square root of lambda. So the solution will be a linear combination of these two solutions. And what you have to do is to find these two constants using the two boundary conditions. Right? It's fine. So if I give you this kind of problem in the exam, you will be able to do it, right? All right. So now, boundary condition. You have what? You have phi 1 is equal to phi of minus 1. All right? So I'm going to replace 1 here. I have C1 cosinus of square root of lambda plus C2 sinus of square root of lambda is equal to C1 cosinus of square root of lambda minus lambda plus C2 sinus of minus square root of lambda. All right? So I'm going to replace 1 to phi and minus 1 to phi. All right? So this is 1. So when I replace 1 to phi, I have 1 here and 1 here. So which means I have C1 cosinus square root of lambda, C2 sinus of lambda. All right? I'm going to replace minus 1. So here I put minus 1. So here I have cosinus of minus square root of lambda. I have minus 1 here. So I have sinus of square root of lambda. It's clear? Questions? So now I have C1 cosinus of square root of lambda plus C2 sinus of square root of lambda. So cosinus of minus of lambda will be cosinus of square root of lambda. And on the other side, you have minus sinus of square root of lambda. Right? So here I have remark. Cosinus of x is cosinus of minus x. And sinus of x is minus sinus of minus x. All right? Right, so when I replace 1 and minus 1 here, and use the formulas, cosinus of x is cosinus of minus x. So cosinus of minus square root of lambda will become cosinus of square root of lambda, right? And sinus of x will be sinus of minus x. So here sinus of minus square root of lambda will become minus of C2 sinus square root of lambda. Questions? It's clear? So on both sides you have cosinus, so this is going away with this one. All right? So from this equation, you see that you have C1 cosine square root of lambda and C1 cosine square root of lambda. So the leftover is C2 sine square root of lambda and minus C2 square root of lambda, right? So I'm going to put this to the left hand side. I have C2 sine square root of lambda is 0, which means that C2 sine square root of lambda is 0. All right? And I'm going to leave it there. Questions? Clear? Right. So now the second boundary condition will be phi prime 1 is phi prime of minus 1. All right? It's clear? Questions? So this is basically the general form of phi. So phi prime of x will be C1 square root of lambda minus sinus square root of lambda x, right? And here I have C2 square root of lambda cosinus of square root of lambda x, right? So I'm going to take the derivative of this quantity, right? So for the second one, what I do is I have to consider the boundary condition phi prime of 1 is equal to phi prime of minus 1. So what I do is I have to take the derivative of this solution. So I take the derivative of C1 cosinus square root of lambda. So the derivative of cosinus is minus sinus, all right? And then there's a factor of square root of lambda outside. So now I'm going to take the derivative of this guy. So the derivative of sinus is cosinus, and I have to have the factor square root of lambda outside. Questions? It's clear? So remark, here I have one. I have cosinus square root of lambda. X prime is minus sinus of square root of lambda x, and this is square root of lambda. And I have sinus square root of lambda x prime is square root of lambda cosinus of square root of lambda x. All right. Now I'm going to replace 1 and minus 1 into this formula. So I have minus C1 square root of lambda sinus of square root of lambda plus C2 square root of lambda cosinus of square root of lambda is equal to, I put minus 1 here, I have minus C1 square root of lambda sinus of minus square root of lambda plus C2 square root of lambda cosinus minus square root of lambda. All right? Questions? So I'm going to use this boundary condition, which means that I have to replace 1 and minus 1 here, right? So when I replace 1, I have minus square root of lambda sinus square root of lambda plus C2. So here I have 1, so I have lambda cosinus square root of lambda. I replace minus 1 here, so I have C1 square root of lambda sinus minus square root of lambda, and here I have minus lambda, right? So here I have all of the square root of lambda. I'm going to remove all of them. I'm going to use this formula again. Cosinus of x will be cosinus of minus x, and sinus of minus x is minus sinus of x. So I have minus C1 sinus of square root of lambda plus C2 cosinus of square root of lambda, and here I have C1 sinus of square root of lambda plus C2 cosinus of square root of lambda. All right? It's clear? Right, so again, I explain again. So here I replace minus 1, but sinus square root of lambda is minus sinus square root of lambda, but I have a minus here, so I have sinus of square root of lambda. So basically, this is the formula that I'm using, right? Questions? For the second one, cosinus of square root of lambda will be cosinus of square root of lambda. So I observe that here I have the same term on both sides, so I can remove them. So this is minus, this is plus, so I have 2c1 sinus of square root of lambda is 0. So which means that c1 sinus of square root of lambda is going to be 0, right? So I have two equations. The first one is this one, and the second is this one. Right? So from the two equations, I conclude that sinus of square root of lambda is always 0. All right? Which means that square root of lambda has to be n pi, right? So remark, sinus of square root n pi is always 0. All right? For n to be 1, 2, 3, 4, 5. So here I have n is 1, 2, 3, 4, 5. All right? So from the two equations, I conclude that the sinus of square root of lambda has to be 0, which means that square root of lambda has to be n pi, right? So those formula are the things that you have to memorize, all right? So another thing that you have to memorize, cosinus n pi plus pi over 2 has to be 0, and it's 1, 2, 3. All right, so those are the things that you have to remember. All right, so I explain again. So in the second case, when lambda is positive, you have sinus and cosinus. So when you have cosinus and sinus, you replace two boundary condition. You find C2 sinus square root of lambda is 0 and C1 sinus square root of lambda is 0, which means that sinus square root of lambda is 0. All right. So to this level, you have to memorize all of the formula of this form. So sinus of n pi is always 0. Yes?
Is the square root of lambda always equal to n pi or only in this problem?
So if here I find sinus square root of lambda is 0, so it has to be n pi. So if I find cosinus of square root of lambda, so if I find cosinus of square root of lambda is 0, right? So I have to have square root of lambda is n pi plus pi over 2.
Okay.
Right? Questions? Other questions? It's clear? Right? So it depends on the solution that you find. And you have to keep in mind all of those formula. Right? In this case, I find sinus square root of lambda, so square root of lambda have to be n pi. But if you have cosinus, it has to be this form or some other. So if I find other equation, I have square root of lambda has to be of other forms. All right. So basically, square root of lambda is this one. So this is the remark. So which means that lambda is n pi squared. All right. And it's going to be 1, 2, 3. All right. So in other words, you have eigenvalue. Which is lambda n is n pi square, and eigen function or eigenvectors will be right. So now we have to find eigenfunctions and eigenvectors. All right, eigenfunction or eigenvectors. So in this case, you have what? You have phi x is c1 cosinus of square root of lambda x plus c2 sinus of square root of lambda x. All right. So this is c1 cosinus of n pi x plus C2 sinus of n pi x. All right? So in this problem, C1 and C2 can be anything. C1 and C2 can be anything. Any constant. All right? So which means that for one eigen function, for the eigen value lambda n is n pi, we have for each eigenvalue, we have two eigenfunctions. All right, so phi n 1 will be cosinus of n pi, and phi n of 2 will be sinus of n pi. All right? So the two eigenfunctions will be this one and this one. All right? So we ignore, which means that we ignore all of the constant. Ignore all the constant. And we keep only the functions. Right? Questions? So I explain again. So in this case, you find lambda to be n pi, which means that you will have eigenvalues of the form n pi squared, where n is going to be 1, 2, 3, 4, 5. Right? It's clear? So the eigenfunctions will be, so in the solution we find C1 cosinus square root of lambda, C2 square root of lambda, which means that you have C1 cosinus of n pi x and C2 sinus of n pi x. Right? So C1 and C2 can be anything. So I can ignore the constant, and I keep only the two functions, cosinus n pi x and sinus n pi x. All right? So for each eigenvalue of this form, n pi, right? So you have two eigenfunctions or eigenvalue, cosinus of n pi and sinus of n pi, which are the two functions here. Questions? It's clear? So, to conclude the end of step number 1.
So we just ignore the case in which it's the cosine, where the n pi plus pi over 2?
Sorry, can you repeat the questions?
Are we just like, it seems like you're just going with the sine root lambda, and not the cosine root lambda equals 0?
Yes, so sinus is
lambda equals something different when it's cosine aspect?
yes. So I explain this again. So what we find is the following. So you find sinus of square root of lambda is 0, and the function is what? Is C1 cosinus of square root of lambda x plus C2 sinus square root of lambda x. Right? This is the solution. The condition is sinus square root of lambda is 0. Right? This gives you n pi. Right?
Right.
So you plug this back to this equation, to this solution. So you have C1 cosinus of square.
Right. So do we not do the same thing with the condition of cosine lambda x equals?
No, we don't find anything for that. We don't find anything for cosinus. Cosinus cannot be 0
Oh, okay. Never mind.
because the boundary condition only gives you sinus.
Okay.
Right?
Gotcha.
So this gives you this one, which means that you have two eigen functions for one eigenvector. Eigenvalue, sorry.
Okay. Good.
Right? So conclusion. When the eigenvalue lambda is 0, you have one eigen function, which is 1. All right? When the eigenvalue lambda n is n pi square, and it's going to be 1, 2, 3. So you have two eigenfunctions. Cosinus of n pi x and sinus of n pi x. All right? Right? Questions? So the conclusion is, this is case number 2, right? This is case 2. And this is case 3. So in case 2, what you find is one eigen function which is 1, and in case 2 you have two eigen functions which is cosinus and sinus. So the basis will be 1 cosinus of n pi and sinus of n pi. So this basis is 1. This is the Fourier's basis, right? This is what we find in the first chapter. So this is the Fourier basis. So in step number 2, you have to expand. Minus x in terms of Fourier series. Right? Because this is the basis. Basically, you find Fourier basis for this problem. All right? So in the second step, you have to expand the source term minus x in terms of Fourier series, and you plug it back to solve the solution, right? And the solution is given in this solution of the practice exam that I put on Canvas, right? So I want to solve this problem because I want to make the connection between eigenvalues, eigenvalue problems and the Fourier series that we learned in the previous lecture. So basically, the Fourier series is a special case of this kind of eigenvalue problem. Right? So sometimes when you solve an eigenvalue problem, you can find the Fourier series basis, but sometimes you don't. So Fourier series basis is just one special case of all of these eigenvalue problem that we study. All right? So you are confident for the exam on Friday? It's going to be on Friday.
Yeah. So on the exam, we're going to have to do step 2 and 3, or is it only going to be solving the eigenvalue?
So the structure of the exam will be the same with this one, right? So the first one is only eigenvalue problem, and the second one is eigenvalue problem plus the Fourier value problem. So you have to find all of this. You have to expand the source term in terms of the basis, and you have formula for the solution. Right? So there are 2 questions, only 2. And then there's also one bonus question. Yes?
So this is 10 coming out of 20?
It's going to be 20, yes.
10, the third question will also be 10?
The last one will be 10. So you can get 30. If you can solve everything.